Every operation in a modern artificial intelligence pipeline is bound by a strict architectural constraint, the token limit. The capacity of an LLM's context window and the financial cost of an API call are directly calculated by the volume of tokens forced through that bottleneck. When engineers pass structured data to these models, they overwhelmingly rely on JSON. It is the standard for web architecture. But JSON was engineered for web browsers, not for token economics, and its grammar is verbose. This diagram illustrates a standard JSON block containing a simple array of 5 user records. To parse correctly, JSON requires an array of specific punctuation. Every curly brace, every pair of quotation marks, and every comma is computed as a token. The cost lies in the repetition. As the highlights shift to target the specific string keys, ID, name, and role, you see them hard-coded into every single individual record in the array. This redundancy multiplies token consumption. In a production environment, this bloat has direct engineering consequences. It reduces the financial efficiency of the deployment, elevates processing latency, and uses up the finite space available in the LLM's context window. Maximizing the throughput of structured data means we can no longer rely on legacy web standards. The pipeline requires a serialization format natively engineered to minimize token weight. That format is Token-Oriented Object Notation, or TOON. It operates as a lossless serialization alternative, built specifically to act as the payload structure for large language models. The primary metric driving its adoption is volume reduction. Across standard workloads, parsing identical datasets through TOON yields a 30 to 60% reduction in total token overhead compared to standard JSON. It achieves this compression by systematically removing syntactical punctuation. TOON replaces curly braces with a strict indentation hierarchy and flattens repetitive object arrays into a tabular structure with a single header. Despite aggressive syntactic compression, the format is lossless. TOON libraries and languages like TypeScript and Python provide bidirectional conversion with existing JSON databases without data loss. By redesigning how the payload is serialized, TOON alters the structural token-to-data ratio. It strips the syntax to the minimum required for machine parsing without sacrificing deep hierarchical integrity. To understand exactly how these efficiencies are achieved, this split-screen comparison maps the refactoring process. On the left is the standard JSON payload. The blank space on the right will map the TOON equivalent. The first pass removes the bounding architecture. The curly braces and structural quotes dissolve. As the nested objects migrate to the right side, they structure themselves using a 2-space indentation, eliminating the need for closing tags. Next, flat arrays of primitives are compressed. The bracketed list of strings slides right and collapses into a single line, featuring an explicitly declared array length at the start, tags 2, followed by the values. The process then targets the most expensive structure in the payload, uniform object arrays. The focus zooms in on the 5 identical keys repeated across every user profile. TOON extracts those keys from the individual objects. They pull away and consolidate into a single declarative array header at the top of the new block, defining the structure once for the entire array. Stripped of their keys, the remaining isolated data values snap into position beneath the new header. They form a comma-separated row for each object. Looking at the final outputs side by side, the result is evident. The right side represents the same amount of structured data, mapped with fewer raw characters. This tabular consolidation removes the structural redundancy of JSON. The result is an operation that maximizes the informational density of every token delivered. For workloads pushing the limits of an AI's context window, engineers can drive token counts lower by altering the delimiters. TOON allows replacing standard comma separations with hard tabs. Tabs provide efficiency because they are a single character that rarely occurs in the middle of a text string. This reduces the need for the parser to trigger complex escape sequences to protect the data. TOON also standardizes data types. Its automated coercion protocols map dates directly into ISO strings and convert mathematically undefined values, like nan or infinity, into nulls. However, formatting is only half the problem. When building enterprise pipelines, attempting to serialize massive arrays of data into a monolithic in-memory string frequently triggers out-of-memory errors before the payload even reaches the API. To bypass this, TOON implements an encode lines function. This allows the system to stream serialized outputs line by line incrementally, rather than holding the entire data block in memory simultaneously. By coupling token compression with low memory streaming, TOON can manage enterprise-scale datasets that would otherwise risk crashing serialization pipelines. When integrating this format into an active LLM query, engineers should not use context window space explaining the format's syntax rules to the model. Because modern models are pre-trained on both YAML spacing and CSV formatting, they interpret TOON as a recognizable hybrid of those two patterns. This interface demonstrates a few-shot strategy. The engineer inserts a minimal 2 to 5 row TOON code block directly into the system prompt as a structural template, which is more effective than long paragraphs of instructional text. When generating TOON from the model, you dictate the exact array header format expected. A single explicit instruction requires the model to use the exact field names and forces it to map the variable n to its final row count. By requiring the model to write that specific length marker, you influence its attention mechanism. The LLM must track its own generated rows to satisfy the structural constraint it committed to in the header. Demonstrating the structural pattern via a few-shot example ensures architectural replication without using the prompt's token budget on extensive documentation. Beyond volume reduction, TOON provides an architectural advantage. Its embedded structure functions as a schema-aware guardrail for AI text generation. Because TOON requires explicitly declared metadata fields, specifically the length markers and the predefined column headers, the format supports strict programmable validation. The parsing engine executes TOON's strict mode decode command. It scans the response, cross-referencing generated rows with the n length marker. Strict mode monitors for formatting discrepancies. Here, the parser flashes a warning. The LLM generated 3 rows, but the header specified 4. This validation layer identifies discrepancies, such as data truncations or formatting errors, before they are written to the database. By leaning on embedded syntax markers, TOON adds a layer of deterministic validation to probabilistic model outputs, preventing malformed data from entering the production environment. Despite its compression ratios and validation layers, TOON is not universally superior. Its value is dependent on the geometry of the data. If a payload contains highly nested, non-uniform structures with variable fields inside every object, TOON's tabular array mechanics provide little benefit. For irregular schemas, a TOON implementation may incur a higher token cost than using minified JSON. This decision matrix charts optimal formats based on data geometry. For completely flat, single-level datasets with zero nesting, raw CSV remains the most compact choice. TOON's primary utility is in processing repetitive, uniform object arrays through token-sensitive LLM application programming interfaces. For software architects managing the constraints of token economics, TOON provides a mathematically leaner and strictly validated bridge between complex data schemas and artificial intelligence.